Alright, today I'm gonna cover 9i, which is the golden ratio. It will link back to uh, chapter 4 with the geometric series and the geometric ratio, and as well it'll still fit in chapter 9 in terms of the algebraic proofing related to geometrical shapes. And let me resize my window because actually on my recording that's gonna be a problem. No. Okay. Also have to remember to share my screen. Let me do that. That's gonna be the way. Okay, so the theorem. It's about all golden rectangles are similar with, when you look at the ratio of the length, so the length is BC and the width is the CD, that's the that vertical part, and it's a ratio of 1 plus root 5 over 2 to 1. Okay, so keep that in mind. That's for the theorem. We look at the actual proofing. So we're going to look at the proofing, determine the value of the golden ratio. We're going to look also at proofing that it is irrational, okay? And also the constructions, how using a geometrical construction you can actually measure the value of it. Obviously will be, as a measurement, it will be an approximation of the actual ratio. Okay, so you construct the way it's gonna be done here. You will construct you have that rectangle, so A, B, C, D. We'll define AD or BD to be the length, and CD or AB to be the width. Hang on, so it did it the other way around, so it doesn't really matter anyway. So what we define now is if BC, sorry, let's do AD. If AD is the length and that's your width, ABFE is a square. So what it means is AE is also equal to the width. So if you subtract the width from the length, that gives you the length ED. Okay? Going back to the previous part with similarities, you'll find out that those two rectangles, so you have A, B, C, D, compared to the tilted rectangle, which is let's call it C, D, E, F, are similar. So what we do is we write the ratio of so the starting rectangle is going to be the image, so it's AD, so that side will be corresponding to the side CD here. So AD over CD is equal to the similarity factor. And we can do the same with, now if we look at the image rectangle, so ABCD, if we look at that length, CD over ED, which is the length of the original rectangle, it's again is going to be equal to K. Using that ratio, we're going to, why can't we just say AD over ED? Because it's not true. We can't. What you need to realize is that we're looking at that. So ABCD is your image rectangle, let's say for that ratio. No, let me rephrase that. Let's say that's your original one. So ABCD is your original, and we're going to put the original length on the numerator, and your image rectangle, the one that you transform, that's going to be similar to the original, is CDEF. So it's tilted, it's turned 90 degrees. Okay, so that length AD correspond to CD, because that image rectangle is turned. So it's not ED, it's not the same side. Okay, so just do that, write those relationships. Then we have defined as AD, CD, and ED. We substitute with the actual values. Now, if you look at what you have, you have two equals, so you actually have two equations. Okay, again, you have two unknowns, which are W and L. You look, the first equation is the first equality, will give you a quadratic. So by doing a cross product, you end up with this expression. Okay, let's move on to the next slide. Now, the second equation, what you could do is either use this expression equal to K, but the simpler one is to use L over W is equal to K. Okay, so we use that second equation, we substitute L by KW, so you end up with an equation, a quadratic in terms of W, you simplify it. So that's the equation, the quadratic equation that relates to the golden ratio. The golden ratio is always positive. When you solve that quadratic equation, you end up with a positive and a negative value. The positive value is that irrational value, which is what you call the golden ratio. Now, we're not going to call it K. K is too simple. They decided to use a random Greek letter, which is phi, P-H-I. So that's lowercase phi. We substitute K by phi. Phi is that the Greek symbol that represents the golden ratio, which is the solution of that quadratic equation. And also, we can relate that to the original quadratic equation. Okay? So it's the same as before with a K, except we just substitute with phi. Okay? Now, graphically, the way you can represent that, it's what you do is you start with your large rectangle. On the left hand side, you create your square. You look at that bottom corner of the square, that is going to be your first point to generate your series of golden ratio. And then you move on to your next rectangle, so you turn it 90 degrees and you end up with that corner by creating a smaller square, and so on, and you continue to infinity, and that pattern is what is generated with the golden ratio series. Okay. Now let's relate that golden ratio to the geometric mean. So if you go back to chapter 4, I just want to go quickly glance over that. You can look at it into detail. It's in your textbook. When you have a ratio of 3 values like that, but you have that C that is common to the two fractions on the side with the numerator and the denominator, what we say is C is the geometric mean of A and B. Now, if you go back to the previous proofing, we had a with the similar rectangles, we have that ratio that had a common value of AE. So that length appeared is equivalent to that C that we have up here. So what it means is we have the requirement, so AE is also the geometric mean of AD and AED, which are the two lengths that you have in the other fractions. Okay. Alright, I think that's it for this one. Alright, construction, geometrical construction, quite interesting if you had some time and you have the proper equipment. So you'll need a ruler and a pair of compasses. What you need to do, so what you do is you start with a line segment AB of a unit length. So to do a unit length, let's say you don't scale it, so you would do something like obviously a unit of 1 meter will be too large, 1 centimeter will be too small. I think to make it a factor 10, 10 centimeters will be a decent size, but you can always use a scale factor anyway. I would use, let me see, I'm just looking at my A4 paper. It's 10. I think 10 is okay. 15 will be better on an A4, but if you're interested to actually construct it, just pick a length of 10 centimeters. Okay, so what you need to do is the first step one is you draw a horizontal segment AB. You set that measurement to a unit length, and the next bit is to draw a right angle triangle, and you draw DB. So that's step 2. It needs to be perpendicular. Use a right angle unless you have a grid paper that could help you out. Now the length of DB is going to be half of AB. So that's the way you construct it. So here, if AB is 10 centimeters, DB is going to be half of that, which is 5 centimeters. Then what you do is you finish your right angle triangle by drawing the hypotenuse AD. Okay? And then what you need to do is you use a pair of compasses. The first circle you're going to draw is going to be centered at D, and the radius, it has to be equal to DB. So that's the first circle that you need to draw. Okay, and that circle will intersect the AD hypotenuse at E. Okay, and then you can continue. You can draw the second circle, which is the centered A to E. But what's important is after you draw the first circle, what you measure A to E is actually your X value. Okay, and using the Pythagoras theorem anyway, you're gonna come up with the same quadratic equation as for the golden ratio. So what you measure, that X, if you take the reciprocal, that is equal to phi, which is the golden ratio. So what you do is you measure your radius AE, you change it to your scale factor, whichever you from your starting AB length that you have set as a measurement. It needs to be a unit. So if it's 10 centimeters, you need to divide by 10 to bring it back to unit length. So what you measure here for AE, you need to divide that value by 10 and take the reciprocal, and I will give you your golden ratio through measurement. So again, that's a way to get an approximation of it. Alright, something out of slightly different, but what's interesting is the proofing. Okay, so the golden ratio is irrational. If you look at the expression, is 1 plus root 5 over 2. Root 5 is an irrational number. So the theorem, that's the theorem. The theorem says the golden ratio phi is irrational. Now, what do you mean by theorem? If you don't remember what a theorem is, it's not like a rule. It's actually, you can prove that it is, there's a proofing, and then you come up with a sort of a rule, but it's coming from proofing. So that's why you call it a theorem. So to prove that the golden ratio is irrational, one technique to be used is you start your statement by saying the opposite. You do your steps with your proofing, and you're gonna come up with a contradiction or an error. And if you come up with an error, then you can go back to your original statement and say that, well, what I assumed from the start is actually the opposite. So to prove that that ratio is irrational, you're gonna start with, you're gonna suppose that the golden ratio is rational. So rational is the complete opposite. Now, if you assume that it is rational, a rational number can be expressed as a fraction. So we can say phi is a fraction. So it's m over n, and the coefficients of the numerators and the denominator are natural number, okay, because again it's a positive number, so we just use the whole number, not the integer. And what we do is we can assume, so we assume that m and n have no common factor, meaning this is the simplest form of the fraction, hence the numerator m is as small as possible. You know that phi is greater than 1, So what we can conclude is m is greater than 1. Okay? Now, if you go back to the golden ratio equation, we have that equation. We substitute phi by the, hang on, no, we're not substituting yet. So what we do is we're making, how does it work out? Yeah, we transpose the negative 1 on the other side. Okay? The first two terms, phi squared minus phi, we can factorize phi, and the remaining factor, which is phi minus 1, we're going to transpose it on the right hand side as a denominator. So we end up with this expression, okay? And now on the right hand side, just that phi, we ignore that one on the left, just that phi on the right, because we assume that it was rational, we can substitute by m over n. We rearrange that fraction, and that gives you n over n minus 1, okay? Now remember, we assume that m is greater than n. So that denominator, as we assume m is greater than n, we have now expressed phi as that expression. We have now expressed phi as a fraction with the numerator smaller than m, because that's n. Okay? And now what happens is you're contradicting the initial assumption of phi. Because there's a contradiction or an error, then we can go back to the previous slide and say, as we assume that phi was rational, now we can say that it's actually the opposite. So now phi is irrational. So that's the proofing. And the structure of it is, when you want to prove, you start with the opposite, you do your working out, you come up with a contradiction, so you can go back to your original assumption and you have proven that it is the opposite. Okay? Alright, so that's it for 9i and chapter 9.
Okay.